This is the first video in Chapter 4, and it's an introduction to discrete probability distributions. This is covered in Mendenhall in sections 4.1 and 4.2. So let's recall what the graphs of Chapter 2 were about. This is the chapter on descriptive statistics, and in that chapter the graphs were frequency distributions. That means that the y-axis gave the counts. So here you have several classes. This has to do with some exam scores. It's organized into a histogram, and the height of each bar was the number of exam scores that was in that range. The graphs that we're going to work with in this chapter and in the rest of pretty much the rest of the course are going to be probability distributions. That means the y-axis is going to give the probability, not the count. I'm going to go a little bit over the notation that's used in Mendenhall. Uppercase Y is the random variable. So it's a variable associated with some random event. For example, a game of chance, okay, the lottery, rolling dice, and there are other random events such as, or you can take as random events, such as whether a child will be born girl or boy. So we see that, or whether a certain component that comes off a machine will be broken or not. So those things are taken as random events. Little y is the particular value of the variable. Okay, this is what he's doing, his notation. Just want to point this out, so because at first a little confusing, you know, big Y and little y. What is this? Y is just the name of the random variable. Big Y is little y is its value. The probability that the random variable takes on the value little y is P of y, just as we did before in the previous chapter. N with y in parentheses is the total number of outcomes that are associated with that value y, and n of all values is the total number of values or outcomes in the entire sample space. So probability again is computed just in the simple way it was done before. Total number of ways that y can be obtained in the sample space divided by the total number of all outcomes in the sample space. And just as before, probability varies between 0 and 1, and the sum of all the probabilities over the entire sample space has to equal 1. The graphs for the discrete probability distribution look sort of like histograms. In fact, in Mendenhall he writes some that do look like histograms. They're done with bars. I think it's better to do them with lines. So here's the probability distribution for rolling a die. The random variable is the number on the face. The values for this random variable can vary between 1 and 6. Total number outcomes are 6, and so here's a table giving the probability distribution. 1, 2, 3, 4, 5, 6. They're all equally likely, so the probability of each is 1/6, which you can see adds up to 1, as it should. And here's the graph of this discrete probability distribution. The y-axis again is a probability, not the counts. And I'd like you to draw the graphs with bars, with lines, and not with bars, because really there's nothing in between. You can't get 1 1/2 or 3 3/4. It's a discrete distribution. Here's a slightly more complicated one. In this case, you're rolling a pair of dice. The outcome will be the sum on the two faces, and it will vary between 2 and 12. Of course, there's more than one way to get several of these numbers. And here's a list. For 2, there's only one way. For 12, there's only one way. But if you look at to get 7, there's 6 ways. 9, there's 4 ways, etc. And I'll write those in a table. So here's the table. This is the value of the random variable. Here are the probabilities. There were 36 total possibilities, so you're just dividing by the total number of possibilities, and they do sum to 1, which is what they should do. And here's the graph for the discrete probability distribution of rolling pair of dice. Okay, and just to reiterate, what's on the y-axis are the probabilities of each discrete event occurring.